Remember, one of the fundamental goals of trigonometry is to look at a triangle and be able to relate the sides to the angles. So we're going to take a look at this triangle and apply the Pythagorean theorem. You probably have learned about this in the past. We're going to take a look at it and see how it can help us understand the triangle, the right triangle specifically, in a simple way. And we'll do two very, very simple Pythagorean theorem problems to just keep us familiar with this theorem. When we look at the Pythagorean theorem, we're looking at the three lengths of a right triangle. When we look at a right triangle, we know we have a right triangle if one of the angles is not drawn with a arc like here, but drawn with a little square. This means that we have a 90-degree angle. The other angles are usually defined with Greek letters, sometimes alpha, sometimes beta, in this case theta and phi. And the lengths are described as A, B, and C. C is specifically described as our hypotenuse, and we can see that our C value, our hypotenuse, is always directly across from the 90-degree angle, whereas our A and B sides share the 90-degree angle as one of their angles. All right, so C is always directly across from 90-degree angle. Our Pythagorean theorem is a squared plus b squared is equal to c squared. So we're looking at this from a length scale. So this is the length A, this is the length B, and this is the length C. And this graphic here is a representation of how we can visually see that this is true. And we'll come back to this in a little bit and graphically show us why a squared plus b squared is equal to c squared. Now, there's a couple of rules about triangles that are useful for us to do some sanity checks after solving the Pythagorean theorem. Usually this is used to solve for one of your unknown sides, and we'll do a couple example problems in this video as well. One of the rules about triangles is that the sum of A and B is always going to be greater than C. And this is not only true for right triangles, this is true for any triangles. And an easy way to demonstrate this is to draw some length A and then some length B, and let's say that these are completely flat. Okay, if it's completely flat, we don't have a triangle, we have a straight line. So in order for me to get a triangle, I rotate this B line, and then I connect these 2 points, and I get my length C. Now we can clearly see that this length C is going to be smaller than the sum of this full length when A and B are completely flat, right? So that's going to be A plus B. So A plus B is definitely greater than that C value. You might say, oh, what if you rotate B more? So if B rotates more, it could be there. And then the new C value could be up here. Well, we can visually see that's even much smaller than the sum A plus B. Now, why is this useful? This is a good sanity check, right? So let's say I solve for the side A using the Pythagorean theorem, knowing sides B and C. And I solve for it, and then I can use the fact that A plus B is always going to be greater than C. So I can check to make sure I did that correctly. It's a common error to define one of your other sides, A or B, as your hypotenuse and incorrectly use your Pythagorean theorem. So this is a good sanity check. Another useful rule about triangles is that the sum of the angles, the sum of the three angles, is always equal to 180 degrees. In this case, we're looking at a right triangle, so then theta plus phi would be equal to 90 degrees. So how can we visually see that this is true? So one way to do that is to take a look at a rectangle. In a rectangle, we know, or rectangle or square, we know that we have 4 right angles, and we know that each of these are 90 degrees. So 4 times 90 degrees is 360 degrees. So a square has a sum of 360 degrees. Sometimes we try to talk about the 3 angles. So the sum of a triangle's angles, and this is a symbol for angles, is equal to 180 degrees. That's another way of saying what we say up here. Okay, so I know that the sum of all 4 angles of a square is 360 degrees. If I split that square in half, I get 2 triangles, right? And they share all the angles in that square. So 360 degrees from the square divided by the 2 triangles is the 180 degrees that we see up here, right? Maybe you're still not convinced. You might say, well, what if I split the triangles in a different way, right? So in this case, I split it from one corner to the other. If I split it something like this, what do I get? I have 3 triangles now, right? So let's say I say 3 times 300, or sorry, 3 times the 3 triangles times 160, or sorry, times 180 degrees. This gives me 540 degrees as the sum of all these angles. Now you might say, oh, well, that doesn't equal 360 degrees of the square. Well, the sum of these angles here are not incorporated into the original 4 angles in the square. So I need to subtract that out. So because that's a flat line, we know that's 290 degrees added together, or 180 degrees. So 540 degrees minus that 180 degrees right there. This gives me my 360 degrees. So that all checks out. So hopefully this proves to you that the sum of my angles is equal to 180 degrees. Now this becomes very useful later on, right? It's not directly useful in the Pythagorean theorem, but these principles are very important when we build rules about trigonometry and when we look at physical systems, right? Engineering systems that the Pythagorean theorem can be applied for, and general trigonometry can be applied for. All right, so earlier we showed you this this cartoon that has the sides A, B, and C, and then the sides are also defined with these squares. Now, there's a specific reason for that. What we're trying to show is this, the square, right? When we try to find the area of a square, we just multiply the 2 sides, right? So this will be A squared, this is B squared, and this is C squared, which means if I can show you that the area of the red C squared square is equal to the sum of the areas of the orange or yellow A squared and the green B squared, then this shows that the Pythagorean theorem is applicable here, right? So that's all we're trying to show. So if I move this C squared over here, I can fill it first with A squared, and then I break B squared into small segments, and we can fill in those components. So a quick visual of how the Pythagorean theorem graphically is also represented. So let's take a look at 2 example problems that define how to use the Pythagorean theorem. So here I have a right triangle. Remember, I have my 90-degree angle right here. Remember, directly across from it is my hypotenuse. I'm going to define that as my C length. And we're given the lengths B and A. 3 inches, and 4 inches. And we're going to try to solve for c. So this one's pretty straightforward. We just apply the Pythagorean theorem here. C squared equals a squared plus b squared. A is 4 inches, so a squared is 4 inches squared is 16 inches squared. B is 3 inches, so b squared is 3 inches squared, which is 9 inches squared. So 16 inches squared plus 9 inches squared is 25 inches squared. So this is equal to c squared. So I can take the square root on both sides to solve for c. I get c is equal to the square root of 25 inches squared, but it could be plus or minus. So this is plus c is equal to plus or minus 5 inches. But since we're measuring a length, plus or minus doesn't make sense. So we just put positive. We will always use positive values for a, b, and c. So c is 5 inches. Now, 3, 4, 5 ratio triangle is a very common one because it fits nicely for a right angle, or a right triangle. And it's just a ratio. So I can say 30 inches, 40 inches, and 50 inches, and that work. Or I can multiply everything by 2. I could say 6, 8, and 10, right? So if this was 6, that'll be, b squared would be 36. If this was 8, this would be 8 squared is 64. 64 plus 36 will give us 100. 100 square root of 100 is 10, which will be 5 times 2. So it's just a scale. You can do scaling there. And trigonometry is all about that scaling factor, right? So certain things, the ratios are what's kept constant, and you can scale it by any factor as long as the ratio is held true. Trigonometry follows that, and we'll see that in future videos too. So let's take a look at a second example problem. So here we have, we're given, again, another right triangle. Here's our 90-degree angle. We can see that our C value is our hypotenuse directly across from our 90-degree angle. We're given A and C lengths. We don't have our B lengths. So just a slightly different problem. Hit pause and see if you can solve this one on your own. You've probably seen this one at some point as well. Okay, so let's solve this together. Hopefully you had a chance to solve it on your own. So c squared is 3 times square root 2 inches quantity squared. So I can separate the two, right? So 3 squared is 9. Square root 2 squared is just 2. So 9 times 2 is 18. So 18 inches squared is my c squared term. A squared is 3 inches squared. 3 squared is 9, so 9 inches squared. And then I don't know what b is, so plus b squared. So I have 18 inches squared is equal to 9 inches squared plus b squared. So I can isolate my b squared term by moving the 9 inches squared to the other side. So I got 18 inches squared minus 9 inches squared is b squared. Subtract 18 from 9, or subtract 18 and 9, we get 9 inches squared. Take the square root of 9 inches squared, we get plus or minus 9 inches squared, square root of 9 inches squared. Inches squared, yeah, sorry, which is equal to just plus or minus 3 inches. Again, we're measuring lengths, so just b equals 3 inches makes sense. So we can do quick checks here too, right? So remember some of our rules. Remember that a plus b has to be greater than c. So we can check. Let's check for this the black triangle first. 3 plus 4 is 7. 7 is greater than 5. So that checks off. At least it satisfies this rule. Doesn't mean it's correct. We can check a squared plus b squared is equal to c squared. That's checking that it's correct. Let's do the same thing here. 3 plus 3 is equal to 6. 6 is larger than 3 square root 2. So it all checks out. All right. So we can take a look now. We build upon the Pythagorean theorem. Pythagorean theorem specifically is looking at the lengths components. In the next video, we'll look at how we define angles. We've defined them in terms of degrees here. You probably know that we can also define angles in terms of radians. And so I know that's a tricky point for some students when they're first learning about angles and trigonometry. So we'll spend a little bit of time looking at that in the next video.